Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and today's video is on regular expressions. It's part of the course Analytic Methods for Lawyers, but it's intended for a broad audience. Regular expressions are a way of searching for and modifying text. They were actually invented way back in 1951 and started becoming popular in the late 1960s, and really it's still a system very much in use. Virtually every modern computer language now has the capability to work with regular expressions using either functions that are built into the language or available in commonly used packages. And although the syntax for describing a regular expression can vary slightly across computer languages, the concepts are really identical. And so once you know how to work with regular expressions in one computer language, working with them in others is not generally challenging. What I'm going to do in this video is to survey pattern formation using regular expressions, and also to show how various Wolfram Language functions can make use of regular expressions. Let's start with some text, and we're going to suck in the Constitution of the United States. We'll get that in there. There it is, we the people. And now, let's just do some very basic pattern matching. This is no more sophisticated than you could do with find and replace in most word processors, but we'll ratchet up the difficulty in a bit. But let's start with the basics. So the first thing is, how do you write a regular expression? And you just write the phrase regular expression, and then in quotation marks you put the pattern that you're looking for. So here I'm going to define a pattern that's going to match anytime it sees an H. And so now, if I say string cases, const is the Constitution, pat1 is this regular expression, it's going to return every time it finds an H in the Constitution. And it turns out there are quite a few H's in the Constitution, 2,045 H's. Who knew? All right. I will grant you fully that is not the most interesting example, but it just shows the syntax of how to use a regular expression in conjunction with string cases, which returns, like cases returns a list of everything that matches a regular pattern, string cases return substrings that match a regular expression pattern. We can also use an operator form in which we defer evaluating what we're looking for. We just specify, okay, here's a function that's going to hunt for H's. So we'll call that function find H. There it is. And now we can use it on the Constitution. And we get the same thing, the 2,045 H's in the Constitution. Well, we can do things that are more complicated than just look for an H. We can look for a sequence of letters. What about TH? And there it is. Turns out there are 1,102 TH's. We can also do alternatives. So supposing we say, I want to know every time you find a Q or a Z. One way to designate that is to put those characters in square braces within the regular expression. And there they are. Turns out Constitution doesn't use Q's or Z's very much. All right, well, instead of using string cases, we could use string positions. String cases returns the actual characters that are found. String positions tells you what position in the strings match those characters. So here what we're going to be looking for is every time the word president appears in the Constitution, it's going to tell us the beginning, what character does the P start at, and what character does the T end at, what position does it end at. So it turns out first time it's used is at character 3,405, and the second time is character 3,413. We could, if we wanted, make a little number line plot showing the position of the word president in the Constitution. And you can see it kind of comes in waves. There's a little dollop there, a little dollop, then a lot of constitutioning. That's probably Article 2 of the Constitution, and then some additional material later. It occurred to me that we might want to see the context for the use of president. So let's take the first 10 times that president occurs, those positions. We'll subtract 20 from the first number, add 20 to the second number. So that'll give us a 41 character window to look at what's going on with calls of presidents. We'll use string take to say bring back those strings. And because we have commas inside, and I don't like nested commas, we'll use a column with dividers to present the answer. So if we do that, here's president. So we've got a vice president. Someone's going to be president of the Senate. And this is about how the bill has to be returned by the president within 10 days. Anyway, you can see the context in which the term president is used. Well, there's other functions that can use regular expressions. Among them is string split. String split is very useful. It basically takes a string and it returns a list of strings having split that string based on some character. Now, by default, if you don't tell it what to use, it'll split on periods. And in fact, I'm going to replicate that use of periods here with this regular expression. You'll notice I don't use a period directly. I have to use this backslash / period designation. And let me explain what that is, because we'll see this a lot. There are some characters in regular expressions that have special meanings. They sort of say, don't take this literally, it means something else. And so, for example, \W means a character that could be in a word, or \S means a white space character. And a period means it's a wild card. A naked period is a wild card. So what if you really do mean a period, however? Well, what you're going to do in Wolfram Language to represent that is a \/ period, and then you're going to preface your \/ period with another \ that says, hey, we've escaped the normal realm of how you interpret stuff. Interpret what follows as an escaped character. So the way you write a period is \/ period, right? So we're going to split our constitution every time it sees a period. We'll take the first 10 examples of that, and then we'll put that in a column with some dividers. So here are the first 10 period breaks of the Constitution, and you can see they're not exactly sentences, because Article 1 period, but many of them are sentences. The other thing you'll notice is that the period is gone. So when you do string split with a regular expression, the thing you're using to split with by default doesn't appear. If you want something to appear, you're going to use an arrow and basically say replace every time you see a period. Here I'm going to say replace it with 3 asterisks. I could also say replace it with a period, and that would restore the period. But we'll do 3 asterisks here. And so now you can see what's happened. You can see that every time there was a period, we've interspersed 3 stars. As I mentioned, you could split on whatever you want. So here I'm going to say split on either, that's what that vertical bar means, a comma or a period. Commas are not escaped, they're just normal commas, but as we discussed before, periods are escaped. So now you're going to see basically every little clause of the Constitution. We, the people of the United States, comma, in order to form a more perfect union, comma, establish justice, comma, etc. Okay? All right, time for a little digression. This is not regular expressions directly, but rather Wolfram Language, like many languages, have come up with a way of intelligently splitting text up into sentences. Because periods are not a perfect way of figuring out when sentences begin or end. They're under-inclusive because a sentence can end with a question mark or an exclamation point. And they're over-inclusive because you can have things that end with periods that don't denote the end of a sentence, like Mr., MR, as an abbreviation, or Dr., DR, potentially, as an abbreviation, etc. So text sentences is intended to be smart enough to do a really good job at that. And let's actually do text sentences of the Constitution. It's thinking, and there we go. And it believes there are 283 sentences in the Constitution. Hard to believe that 283 little sentences could generate so much controversy and law over 230 years, but they do. All right, one other thing you can do is text words. Text words basically also uses artificial intelligence to try and figure out word boundaries, which are again roughly approximated by where spaces are, but not precisely. So we can basically say, take our text sentences and break it up into words. And so there it is. We, the people of the United States, in order to form. Okay? And it's saying 283 because it's still keeping the sentence structure, so there are still 283 sentences. If I were to determine the length of each sentence, here's what we could do. How many words are in each sentence? We'll map length over the text words of TS, and it's going to tell us that they vary. I suspect these sentences are things like article or section or something like that. Looks like we've got 144 word sentence in the Constitution. Looks like that might, what's this? 429 words. I bet that is the powers of Congress. Should we check? I think we should check. So let's take the position in this of 429. This is a little bit cheesy, but I'm going to okay it. All right, so there we go. And it turns out to be the 52nd sentence. So if I say, what is TS 52? Yep, it's the powers of Congress. Things like the Commerce Clause, post roads, bankruptcies, etc. All right, so much for con law in the middle of an analytic methods video. On we go. So another command that can use regular expressions is string match Q. And string match Q is very much like match Q. Match Q looks at an expression and sees if it matches a particular conventional Wolfram language pattern, like an underscore. String match Q looks at a string and sees if it matches a string pattern, which is often generated through regular expressions. There are other ways of doing that. I'm not going to cover them in this course because I think regular expressions are a more common method of generating patterns, and so I think it's more generalizable knowledge. Okay, so let's look at this. Here's our text. The rain in Spain falls mainly on the plain, and what we want to do is say, hey, this matches. If there's some text, we'll come to this period plus in a moment. I realized there's no perfect order in which to present this material. It's sort of a seamless web, but this just means there's text before. Then the vertical bar means alternative. So if it sees Spain or France, it's cool. And then it could see stuff afterward. So let's see if this matches. And it does match. Okay, because there's Spain. And Spain is one of the things it needs to see. All right, those parentheses are necessary, however. What would happen if I didn't use them? Here we have the same pattern, but I left off the parentheses. And you're going to see it generates false. Why does it generate false? Because it's basically saying, I'll take everything to the left and I'll look for that, or I'll take everything to the right and I'll look for that. Well, the stuff on the right it's never going to find because there's no France here. And the stuff on the left it's never going to find because there's stuff after Spain, and I didn't put anything in there to capture that, and that's why it's generating false. Okay? On the other hand, if I put the text as France mainly on the plain, I kept this same regular expression, it will match because it starts with France and then there's more stuff. Well, you know how every word processor I know of lets you do find and replace? Well, you can do find and replace with regular expressions. For example, here what I'm going to do is I'm going to create an operator that says, if you see the phrase provide for, turn it to secure anytime in the Constitution. And so if we look at this, we're going to see that what used to be the Constitution, we the people of the United States, in order to perform A more perfect union, establish justice, ensure domestic tranquility. Originally, it was provide for the common defense. However, I have edited it to read secure. So my little committee of style and my regular expressions has managed to change things. Now, you can do a lot more with string replace. We will see that when we discuss capturing, but we really need capturing before we can do more sophisticated string replacement. Pattern classes. So yes, you can build your own patterns with regular expressions, but there are a number of pre-built patterns that are very useful. Supposing, for example, I want to match anything that's a digit. We're going to use backslash, that's our escape warning, and then backslash D, that means a digit character. So if I say string cases, constitution, regular expression, backslash D, that means I want to capture any digit that's in the Constitution. You wouldn't think there would be too many of them in there, but let's see. Well, it turns out that there are a number of digits in the Constitution, and there they all are. So, I might want everything that's not a digit, that's followed by a digit, and then that's followed by something that's not a digit. And oftentimes in regular expressions, to denote the opposite of something, like the opposite of little d for digits, is big D for not digits. So let's see how many times we see that kind of a sequence. So here's one where it is something that's not a digit number 1, and a period that's not a digit. Okay? Or here's one, something that's not a digit that we can't see, the number 3, and then the letter D. In fact, if we do this in input form, we'll see a little more clearly. See here all those little spaces? That's the backslash capital D that we're starting with. And in fact, I think I'm going to leave the code with input form. I think it's a little bit clearer that way. All right, well, one thing I could do would be to look for every word character in the Constitution, and I could then basically take an inventory of every word character in the Constitution and then reverse sort them. So anyone want to bet what the most popular letter in the Constitution is? It's E-T. This is pretty standard for English. So those are the letters of the Constitution. Another class you could look for, you can get more complicated classes. Like let's suppose I want the class of anything that's punctuation. I'm going to use this square bracket, colon, punct for punctuation, colon, square bracket, square bracket. If I want anything that's not punctuation, I'm going to insert a caret between the first and second square brackets. So here, let's find out what the most popular piece of punctuation in the Constitution is. I think it's a semicolon-rich environment. Commas win out heavily over periods, but semicolons get the bronze medal, and then there are a few quotation marks. There's even an apostrophe. Another very useful class is white space. White space is denoted by a lowercase s, and so here what I want to do is I want to find anything that's the letter A, followed by white space, followed by a bunch of word characters, that's what that plus means, and followed by white space. So let's see what qualifies. And I'll count how many of them there are, and we'll sort them. All right, so it turns out a president, there are 9 of those, a majority, there are 7 of those, a vice, there are 3 of those, etc. So now I'm using a little more complicated patterns to help me find text, and I'm using these kind of classes of characters of, for example, here I'm using word characters, here I used punctuation. All right, well, I realize I've snuck in repeats on you without really explaining what they are, and I apologize. I do think it's kind of a seamless web problem. But let's look at the 3 basic patterns that describe the way something might repeat. The first pattern I want to talk about is the question mark. And the question mark means that the text immediately preceding it is optional. So it will match persons if it sees it, but if you just give it person, it will match that as well. And let's see what we pick up when we do that. Turns out there are 9 persons in the Constitution and 18 persons in the Constitution. All right? What if we insist that the pattern in question repeat at least one time? It's not optional. You got to have it at least once. So the way we're going to specify that is with a plus sign. So this means I want to see at least one word character following man, and as many word characters as it sees, it'll grab those and we'll count them up. So we have mander, manned, manner, mancipation, and manufacture. Those are all the patterns that match. Well, what if we want the pattern in question to repeat 0 or more times? Now, you might think that's like the question mark, but not really, because what we're looking for is instances in which we're going to capture multiple copies of it. If there are multiple copies of, for example, the same thing that precedes it. So that's not very clear, but let me try that again. So here you see a //w, a word character. So if I see I followed by URE, it'll take that because it's a star. But if I see I followed by lots of word characters and then followed by URE, it will take that as well. On the other hand, if I see I followed by lots of word characters and then we see XYZ, it won't match because the URE part won't match. And so what we match is ensure, islature, legislature I assume, iture, isure, I'm not sure what isure is, and illure. So that's what the star does. It says grab as much as you can, but you don't actually have to see it at all. Finally, one other fine point, which is you can actually specify how many times you have to see something. So what I'm saying here is I want the letter W followed by anything that isn't a comma. Okay, that's what that caret means. Caret means not. W followed by anything that's not a comma, repeated 5 to 7 times, and then the letters AN. So let's see if that ever occurs in the Constitution. And it does. We have within an, we have WS of an, and we have withstand. So when you want to restrict yourself to a certain number of repeats, you can use curly braces. You've probably used wildcard searching in text processors, and oftentimes you use a star as your wildcard. In regular expressions, the general wildcard character is the period. That's why we have to use / period if we mean a real period. So here, basically, I'm saying find me any word in which a single character lies between the T and the E. And we get the, twee, T blanky, toll, etc. Or it might be I just want an A that's followed 2 characters later by an E and then an R. And that's that those 2 periods there are, that just means any 2 characters will match. So there we go. Here's an A, 2 characters, ER. An A, 2 characters, ER. Not only can we match traditional text using regular expressions, we can turn, as long as we can represent something as characters, we can use regular expressions to match. So what if I took the first 1,000,000 digits of pi and I looked to see, are there occasions in which the digit sequence 0, 1, 2, 3, 4, 5 appears? So to do that, I'm going to tell Mathematica to compute pi out to 1,000,000 decimal places and then convert that into a string. All right, so here we go. Done. 1,000,000 places of pi converted into a string. And now let's see if there's anywhere in that 1,000,000 characters that matches the regular expression 0, 1, 2, 3, 4, 5. I'm going to put repeated timing here just so you can see how fast regular expressions work. This computes the average time if you run the code like 10 times. And so in less than 1/100th of a second, it has indeed found that there are 2 occasions in the first million digits of pi where we see 0, 1, 2, 3, 4, 5. We can also use regular expressions to search genetic data. Here I'm going to get the gene for BRCA1, it's a breast cancer gene. It's a very well studied gene. And let's download that. Okay, so there we are. It's 81,155 characters long. And now let's see, I don't know if you're familiar with the movie Gattaca. It was a famous movie, maybe 20 some years ago. Anyway, let's see if the string Gattaca is anywhere in the gene BRCA1. And indeed, the string appears on numerous occasions, and you can see how fast it just churned through that long string. You have some options when you are using regular expressions. One is whether case matters. Does capital T match lowercase t? The default is that case matters, and therefore a capital T in a pattern will not match a lowercase t. But you can change that, and the way you change that is by adding the directive $I for ignore case. All right, so we just put that in right before what we're searching for, and now it should match any little t or uppercase T, and we'll get a count of how many of each are in the Constitution. And the Constitution, you'll be pleased to know, has 3,771 little t's and 174 big T's. All right, so now we want to deal with how do we deal with when there are new lines in text. Now, actually, our Constitution, the way Wolfram formatted it, there are no new lines, but oftentimes you do have new lines in text, and you need to know how is matching going to work across lines. So here's a sample piece of text here. This is sentence 1, new line, that's the \n, and this is sentence 2. So let's put that in there. Let's form a pattern string, which is going to be anything plus the letter sentence plus anything plus the word and with a capital A, and then more stuff. And now I'm going to search for that regular expression. And you might think, well, it should match, because here's sentence, here's more stuff, and here's capital and. But the fact that there is a new line here is going to bust the search. It's not going to let our wildcard break the /n. And so when I evaluate this, it says I don't find a match. Well, if I do want it to just treat new lines like they're not there and bust through them, what we do is we add the option $S before our regular search pattern. I've done that here with string join. Here, let's just execute it in place. So that's what it looks like. And now let's see if it matches. And hooray, it does. So far I haven't done anything very sophisticated with the sort of search and replace, but oftentimes we do want to do something fairly sophisticated, and we kind of want to create a function of what it is that we've captured. So to do this, I think it would be helpful for me to discuss string join and string template. So string join, you actually just saw it. I had to use it up there. But it's just a way of putting pieces of text together. So here's the string join of the cat in hat and the cat in hat. You can also use an infix operator. So you can do this with the less than sign and the greater than sign and just put it between what you want to join up. I can't say I'm a big fan of that syntax, but there it is. There's also a function string template that I find extremely useful, and I think really the best way to see it is with an example. Here's our template. There were backtick 1, backtick chickens crossing the road on backtick 2, backtick. So this is sometimes called string interpolation, and it essentially creates a function in which the first argument goes where that backtick 1 thing is, and the second argument goes where that backtick 2 thing is. So if I give it 6 and Tuesday as the arguments, it's going to say, oh, we have a new string. There were 6 chickens crossing the road on Tuesday. You'll notice I don't have to use numbered arguments when I use string template. I can use named arguments. So here it's backtick how many, and here it's backtick day. When I do that, I need to have an association in which the keys match up with what's in between the backticks. So if I run this, I get the same thing. There were 6 chickens crossing the road on Tuesday, presumably to get to the other side. All right, with that out of the way, back to business. So sometimes, as I said, we want the output of our regular expression search to be a function of whatever we found. And the way we're going to do this is we're going to, here's string cases, we're going to create a rule. The left-hand side of the rule is what we're looking for. And the right-hand side of the rule is what we want to transform it into. So let's look at this more carefully. Do you see I've got 2 sets of parentheses here? One capturing the C and then word characters, and the other capturing B and then some word characters. Those are going to translate. This first parenthesized stuff is going to be captured in $1, and the second parenthesized stuff is going to be captured in $2. So what we should get is a list of every occasion in which we're going to look for sentences or text which has the something and then some space and then something, and we're going to create a list in which the something is the first value and the something is the second value. All right, and there we go. Congress by, Constitution by, Constitution by, Constitution by, Constitution by. So that's one way of creating a function out of what you've captured. We can be a little more elaborate. Like here, supposing I want to capture anytime we have something starting with a capital C, and I want that's prefaced by the, and I want to say the Constitution uses the definite article the to precede backtick, captured backtick. And what are we going to fill in? How are we going to interpolate backtick, captured backtick? We're going to say we have an association here. Captured goes to $1. What's $1? $1 is that first parenthesis stuff that we captured. So if I do that, we see the Constitution uses the definite article the to precede Congress. The Constitution uses the definite article the to precede chief, etc. So we're starting to use a little more sophisticated methods. By the way, what's this for about? This for is just saying, it's a command to string cases. It doesn't have anything to do with regular expressions. It's just saying, produce only 4 outputs, please, stop. We can also have, as I said, multiple captures. So let's look at this. This is a little more complicated. Our first capture starts here, and it doesn't end until all the way over here. So that's our first capture. Our second capture starts here and ends here, and our third capture starts here and ends there. And so what we're going to do is we're going to output an association where everything, I say all, is that full first capture. Before is the thing that comes before the word supreme, and after is everything that comes after the word supreme. So this is an example of overlapping captures. All is the Supreme Court, before is the, and after is court. Here, all is the supreme law, before is the, and after is law. Okay, well, let's put our learning to some use. Supposing we have a bunch of text, and here the text I'm going to go for is the Trump Twitter archive, which contains all the tweets of former President Donald Trump before Twitter closed down his account. I've got it here on my hard drive, and I'll post it on the Wolfram cloud for use by viewers, at least in my class. And so we're going to snarf up all of Trump's tweets, put it in a data set. All right, we snarfed them up. And we could, if we wanted, make a word cloud of those tweets. Let's actually look at the data set, see what it looks like. And so you can see there's the ID of the tweet, there's the text of the tweet. It's going to tell us whether it was a retweet, whether it got deleted, where Trump sent it from, how many people favorited it, how many people retweeted it, what date it was sent on, and I think is flagged means whether Twitter flagged it for some things that it didn't care for. So that's what we've got. Let's actually hold off on our word cloud for a moment. Let's do the following. Let's use select to eliminate any of his retweets. I'd like to know at the moment just what he originated, not what he retweeted. So we're going to select his retweet, and we're going to say if that's F, false, we don't want it. All right, so we'll call this the originated tweets, and instead of there being, how many of them were there to begin with? We originally had 56,571 things in his Twitter account. We're down to 46,694 things in his Twitter account. Well, you know how people in Twitter, they at other people sort of as a call out, sometimes for good things, sometimes for things that they don't like. And so let's look at who President Trump called out by adding. So we're going to create a regular expression, and we're going to say start it with at and then some word characters, and that'll be the end. So that's our at pattern. And now let's go through our originated tweets. We're going to map string cases over every line of those tweets looking for the at pattern. Once we find that, we're going to unwrap it out of the data set with normal, and then I don't want it really to be a list. I just want it a nested list, at least. I want it to be a flat list, so we'll flatten everything. And here I've written the program in the old school inside-out way. I could have written it in the new school originated / and then composed functions, but I guess I did it the old-fashioned way here. So this is what's been added, and we can see these are various people: Senator Ted Cruz, Senator Ron Johnson, Fox News, GOP, the Brazilian president Jair Bolsonaro, etc. We could also find out how many times entities are added, and then we'll sort the results from high to low. So we'll see who do you think Donald Trump added most? Himself, real Donald Trump. Then Fox News, then Barack Obama, Fox and Friends, The Apprentice TV show, CNN, Mitt Romney, Sean Hannity, the failing New York Times, etc. So his whole cast is there. I guess we could take his favorite words and put them into a word cloud. So I guess now we can do that. So to do this, I think what we're going to do is we're going to say map text over originated, okay? And then once we have that, we're going to get it out of the data set, so we'll say normal. And then it's a bunch of text. I think we do better if we put all the text together. And so I think what we can do is string join it all. Let's see what happens if we do this. We get a very long string. That's okay. And let's now say, let's word cloud that. Oh, look at this. Foolish me. Stop. I have the code right here. All right, so here's the code. And actually, it's very similar to what I just did. Start with originated, get the text field, normal it to get it out of the data set, string join it, and make a word cloud out of it. All right, so I managed to recreate on the fly what I'd earlier written. And this might take a moment, a lot of text to parse. I'll pause the video while it's figuring it out. And there we are. What's at the center of the Donald Trump word cloud? Real Donald Trump, and President Trump, and great. So kind of what you might expect. That's what the word cloud shows he tweeted about most. Well, we could also figure out what tweets appeal to the most people and whether there are any special words in them. So what I'm going to do is I'm going to take each tweet and assign to each word in the tweet a number, a value that's equal to the number of times that the tweet was favorited by followers. Remember, we have a favorited column. And to do this, I'm going to put all the words in lowercase. I'm going to delete any stop words. Those are words like the and am and were and how, sort of the boring, I don't know, sinews of English rather than the interesting stuff. And then I'm going to add up all the points each word received. So here's the code. It's a little bit elaborate. Basically what we're going to do is we're going to go through this pattern of deleting the stop words, then looking for text words. Text words, remember we saw that earlier. It looks for words. We'll put all the words in lowercase. And then the merge total thing is going to add everything up. And reverse sort will give us the words words ranked by how often the tweet surrounding them was favorited. This does take maybe a minute or two to run. I'll start it now, pause the video, and return when it's done. Okay, so it did take a few minutes, but here we are. And it turns out people like when he uses the word great. People just thank country, news, big, president, fake, etc. And saying unceremoniously really didn't help so much. All right, let's look at the steal. So let's, remember President Trump made various claims that the election was stolen, had a lot of tweets about that. And so let's look at variants of steal. Here are my alternatives: steal, stole, and stolen. And now let's go through originated. We'll look for all positions in the text that where there is the text is a string and it matches the steal regular expression. And we'll flatten those and we'll see the variants of things he said about the election being stolen. So though that phrase was used 131 times, and we can make a timeline plot of every time that Trump claimed that something had been stolen. And so here the code gets a little gnarly, but this is to get dates out. The dates are not really in a form that Wolfram likes, so we got to turn it into the right form. But if we do this, it takes maybe a few moments. All right, and we're done, and you can see there's a flurry of activity in late 2019. If we hover over this, I believe it will tell us, should tell us what the tweet was. Here we go, come on. They are sending out, in the legal late night coup, here's one. Let's look at this one. We believe these people are thieves. The big city machines are corrupt. This was a stolen election, blah, blah, blah. All right, so that's something you can do. And while Trump's tweets may not be of immediate interest, imagine this is a bunch of documents that you've gotten from your adversary in litigation. Well, what other things can we do? We can get email addresses out. Here's an elaborate regex for an email address. You can, it's going to need an @ sign. It's going to need certain characters. We're going to ignore the case. And we can see, did Trump ever stick email addresses in his tweets? And it's going to turn out he did, but not too often. So those are the only email addresses that we could match in the Trump tweet archive. Okay, one final thing we might look at is citations. we could actually find citations. So here is a here's a pattern for a Supreme Court case. It's going to have 1 to 3 digits for the volume number, some space, a U followed by a period, and then sometimes people put spaces between the U and the S, even though they really shouldn't. Nonetheless, they do. Here's a capital S followed by a period, followed by more space, followed by a 1 to 4 digit page number. So that should do us pretty well in spotting US sites. I'm going to import a recent case that was decided by the United States Supreme Court. I've downloaded it to my own notebook, but I'll also post it in the data site for the course. So we're going to snarf up the case of Google against Oracle. It's 236,000 characters. Right, here's where I got it from originally. I guess we don't need that code anymore. And what we can do is we can look for anything in the Google string that matches the SCOTUS sites. And we're going to find out that I've done something wrong. All right, well, maybe this will be instructive. I don't usually let you see my boo-boos. I just fix them behind the scene. But let's look at this. Do you see this pattern here? This says a digit, and then it says plus, and then it says 1 to 4. But that's not what I mean. What I mean is digits of length 1 to 4. So let's try that. And now let's look for SCOTUS sites. And look at that. We pick them all up. All those sites to other Supreme Court cases. I might want to, you see how there's all this ugly space in here? I assume Cornell's going to fix that up eventually. But we can fix that. Here's a different, we're going to capture this number. We're going to capture the last number. And basically, this capture goes to number 1, this capture goes to number 2, and I'm just going to stick US in between them. So now, with better SCOTUS sites as my pattern, let's run string cases on it, and look, that's much prettier. And here's another fun thing we can do. We can use some of our work on unsupervised learning, and let's just get 2 digits. One digit is the volume number, the other is the page number. So we'll get examples of those. And now let's learn the distribution. We can learn a distribution of volume number, page numbers. I'll remind you these are all integers. And in a moment we'll have a learned distribution. All right, we do. And now let's create 10 random citations, and we will conform them to proper form where it's volume, US, page number, etc. So let's see. Here are completely synthetic US citations that, frankly, I mean, if I saw this, I wouldn't know that there was anything obviously wrong with them. So we've just scratched the surface of regular expressions. It's basically one of these enormous subjects. People spend their lives crafting them. It's kind of a fun exercise, but they're essentially a language of patterns, of string patterns, and as such they can be used in a variety of text processing tasks, or really any process where the data can be represented as a string. Thanks so much.